días a todos. Bienvenidos a este 45 aniversario del CIATEJ. Me voy a permitir compartirles una diapositiva donde voy a presentar al doctor Guilherme Lanzi Sassaki, que es nuestro invitado externo. Él es un investigador brasileño que actualmente ocupa el puesto de profesor asociado 4 en la Universidad Federal de Paraná, que se abrevia UFPR. Es farmacéutico industrial egresado de la UFPR en 1997 y obtuvo el doctorado en Ciencias Bioquímicas por la UFPR en 2001. Actualmente tiene el reconocimiento de productividad de investigación del CNPq nivel 1C, que es el análogo al SNI en México. Es miembro afiliado de la Academia Brasileña de Ciencias y hasta abril del 2020 tiene registrado como coautor 197 publicaciones con un total de 3.956 citas y un índice H de 34 en la base de datos del Web of Science. Sus áreas de especialidad es principalmente en bioquímica, con énfasis en química de glicoconjugados y síntesis de carbohidratos, así como el análisis estructural de glicoconjugados y lípidos de diferentes fuentes, actividad biológica de carbohidratos naturales o sintéticos, RMN de compuestos orgánicos, principalmente carbohidratos y lípidos, espectrometría de masas de compuestos orgánicos, mismos carbohidratos y lípidos. Ahora voy a dejar de compartir. Para mí es un gusto recibir aquí al doctor Guilherme. Antes de cederle la palabra al doctor Guilherme, quisiera mencionarles a todos los asistentes que para realizar las preguntas las hagan a través del chat de Zoom. Y yo iré leyendo las preguntas una vez que se haya terminado la presentación. En caso de que no nos alcance el tiempo, estas preguntas se las haremos llegar al doctor Guilherme, quien posteriormente nos apoyará respondiéndolas. Les agradezco su presencia. Muito obrigado, Guilherme, por aceitar o convite para dar palestra no aniversário do CIATEJ. Thank you very much, Guilherme, for accepting this invitation to give a talk on the anniversary of CIATEJ. You can share your presentation, please.
You see me, Jorge?
I see you.
Okay. And the panel of founder, it's okay?
It's okay. You can put in complete mode.
Let's see. Ooh.
If you can, it's okay. We can see.
I'm trying to put the founder on, but I don't know if it's okay. Let's see. Okay, the video. You see me?
Yes. Hi, Guilherme.
Hi, Jorge. Hi, everybody from CIATEJ. It's a great pleasure to be here. And I will say that my last time in Mexico was in 2020 and started COVID and coronavirus. So it's nice to see that everybody is in great shape, and I hope that everybody is very healthy. And it's a great moment for me to show my work that we did in the last year and some results that we obtained using NMR and also carbohydrates. And I focus my presentation, and I will share my presentation now with you. And let's see the laser point. I will stop but everybody's seeing the presentation?
Yes.
Okay. So it's difficult because I'm seeing just this screen, and I'm not familiar with Zoom. I'm always, all the time, I'm using Teams. In this talk, the pointers, it's okay now. In this talk, I will focus my presentation to show to you the structural analysis of carbohydrates by NMR from glycobiology to new applications. And I divide this presentation in two topics. First, I will talk about the carbohydrates in solution for beginners and NMR users. And after, I will talk about the glycans and polysaccharides by NMR and how they come from glycobiology that we saw in biology systems and like fermentation, and also from extraction, and apply this structure in to see the biological activities. And I will focus the presentation in these topics. Well, first, everybody knows about a little bit about NMR. The NMR is a very good analytical tool to investigate the structure of many organic compounds, and of course other compounds, inorganic compounds. But in this talk, I will focus in this behavior of the molecules in solution, because I'm interested to understand how these molecules are in the space, but in solution, not in solid state. Because some phenomena like dynamic properties, of course, 3D conformation are very, very, very important to understand how a structure can interact, or how this structure are affecting the surroundings, and also by the anionic cations and anionic ions, and of course in the water, because many of these contacts are made by the contact about the molecule together the other molecule, and there are some interaction between them regarding to water molecules, and of course the cations and anions in the solution. So a small molecule has a fast tumbling in solution. High molecules or molecular mass like proteins, they are slow tumbling in solution. And when you see this effect in the spectrum, we can first observe the FID, and we see that the FID is very long and decay the frequency time domain, and we can see that the frequency is reaching the equilibrium, and this equilibrium has a time, and this time is very long for small molecules. So these small molecules has short correlation times, and after applying Fourier transformation, we can see that the peaks very high and very sharp. When you saw these big molecules like proteins and polysaccharides, other macromolecules, we can see that these molecules are slow tumbling, and the correlation time is higher. So the FID becomes very short, and after the Fourier transformation, you can see that the peak become broader. Of course, we can alter and define another solvent that's more viscosity for the molecule, like others, but interesting when you are looking for interaction, we choose the solvent, that's water, but you can choose another solvent. And you have for a small molecule that is fast tumbling, another effect. If you choose a viscous solvent, the peak become broad, and of course the feed will be also short. So you can determine the properties, the dynamic properties of the molecule using the correct solvent and also the proper temperature. In this figure, you can also see that there are other forms of to interaction that the molecules in solution. But we can see here in the last panel here that if you have a small molecule that interacts very tight with some other molecule, like a membrane, if this molecule interacts with membrane, for example, this structure become very rigid in the system, and the signal disappear, and you are out of the NMR time scale to observe a signal. This is very common when you are looking for very, very, very big molecules. And of course, you can see the effect in the spectrum. So normally you don't have the signal when you have this type of characteristic system. But you can look also for the dark state of the system. If you excited this system applying the correct radio frequency, you can see the free state that are not observable in certain conditions. Because this NMR start to be a great tool to observe complex systems and protein-protein interaction, and of course nanoparticle interaction with cells and other real systems. You can look for the dark state by exciting the molecules in real state, and you can see what occurs in the molecules that are in the free state, the small ones, okay? But if you want to look this at this condition, it's impossible. You are out of the NMR time scale because the T1 is very short and T2 is more short than T1. So the peak became very broad and you cannot see the signal. Well, another property that you can use in the NMR is the T1 and T2, because these times T1 and T2 are very related to the size of the molecule, and you can see what is the behavior in the dynamic system that you are studying. So for small molecules, the correlation time is short. So we will see that T1 is high, and of course T2 are also high. These two parameters are very important to see if in the structure you have connections and some moieties that are more flexible or more rigid in the system. So we can determine what moiety of the molecule can be more flexible in the system. For intermediate molecules like oligosaccharides and small peptides, we have intermediate motion, so the correlation time is not so short, but T1 and T2 are like similar, okay, they are similar, but T1 is not so long and T2 is together in the system. So T1 and T2 are like the same. But when you have slow tumbling molecules like proteins, that the correlation time is very high, T1 is very long, and T2 is very small. It represented here in this case. If we have small T2, short T2, we will have Brown's peak or no sign. This is the limit to see the NMR signal. We have to understand this because in many times we're trying to observe some signals, but you are out of the NMR time scale to observe the transitions. Here we have an AG1 NMR spectra, because in NMR resonance, we have some peculiarities for the nuclei to be excited and to be observable by NMR phenomenon. So, of course, we work with hydrogen and 31 phosphorus, C13 NMR, and 15 nitrogen. These nuclei are excitable for radio frequency and able to produce NMR signals, because in the quantum physics, the transitions and the spin, nuclear spin, are half. Because there are nucleus that are sensitive to NMR spectroscope technique. And in this case, I will use the most important nucleus for NMR spectra, because hydrogen is very abundant. Hydrogen have a nuclear spin of half and is very excitable, and the magnetic constant is very high, sensitive for hydrogen nuclear, different from carbon C13 and nitrogen 15. And in the spectra, we can see three examples, real examples of the size of the molecule. In the first, we have the lactose in milk, breast milk, human milk, that was extracted some oligosaccharides separated from the proteins, and we can see the difference in the spectrum. Here, I will presenting that this spectrum is saturated, pre-saturated, to avoid the residual water peak. So we have an increment in the pulse that we can eliminate the residual water peak in the spectrum. And we did the same for the other that are on the bottom. In the lactose, well, this is milk, and we can see the signals of the lactose. This signal here is around 40.5 ppm, that represent this hydrogen here on the molecule of lactose. This signal here is around 5.25 ppm, that represents the hydrogen here of the free reducing end of the glucose unit from lactose. So we can have here the galactose, no reducing end, attached by a glycoside linkage from this carbon to carbon 4 of glucose. And we can discriminate here this linkage bound by this signal here. So we can cover all the signals looking in for a fingerprint, or you can cover all the structure analysis to characterize another structure. In the bottom, we have another example of a high molecular weight compound. This is heparin. Heparin is a glycosaminoglycan, and this glycosaminoglycan is a polymer, and this polymer is around the 50 kilodaltons, 15 kilodaltons, so it's very big for NMR, but we can see the signals and the effect of the slow tumbling. We can see that the peak become more broadened, and they are different from the oligosaccharide that are a small molecule that fast tumbling. The shape, the linear shape of the peaks are more broadened for the polymers, and we can see some features about the dynamic properties. In this case, we can see the signals that are characteristic from the heparin. This is the amino group from the units that are glucosamine, sulfated in 2, 3, and 6 position. And we can see also the hydronic group. This is a acidic sugar that are in the glycosaminoglycan. That is sugar here. Sorry, this is the hydronic sugar. So we can discriminate in this spectrum the disaccharide unit that are the main component of heparin. And of course, we can look for more examples and more detail in the spectrum to see the structural features from heparin. Another in the middle, we have 2 or more components with different molecular size. We can see the oligosaccharides here because the peaks are more sharp. And also we can see the protein by the broad peaks. So we have a lot of protein in milk, and after the purification, there are residual protein together the oligosaccharides with medium size. And we can say that the oligosaccharides with medium size are together, and the purification was not so efficient. But we can see the protein content here, protein here, protein here. The peak are very broad. And for instance, we can also see here the sialic group of neuraminic units that are in the oligosaccharides of the milk mixture. And they are very, very important because many viruses link to the sialic acid. And in this case of the milk, they are used as a first immune system for the inborn kids, okay? In the middle spectrum, we can see that there are very, very, very information that we can work and determine more characteristics of this mixture. We see also the fucosyl units that, because the peaks are in the 1.3 ppm, that are characteristics of these fucosyl oligosaccharides that are in human milk oligosaccharides. And of course, the sialic acid and the presence of N-acetyl glucosamine, and of course, and also N-acetyl neonaminic acid. This peak is related to acetyl groups that are present in some carbohydrates, like in glycosaminoglycans. And we can see this in heparin, because in heparin we have the N-acetyl group that has but it's not here, but you have also acetyl groups in heparin. In this position of the glucosamine, in some regions of the heparin, you have acetyl instead of sulfur group of sulfate. So we can see here that heparin also have an acetyl group. Well, to determine a structure by 2D NMR, we use the classic routine that first we use a nitrogen spectrum, the 1D NMR, to see if the structure are pure. And if you need to do some purification or some experiment in the lab to produce a good molecule to study the conformation or the structure, or to determine the structure of the molecule. But the main tools that we use to perform this, and of course, because we need less amount of sample, around 1 milligram and 100 micrograms of a small molecule or medium molecule, we can do first the COSE spectroscopy. COSE is a correlation type homonuclear hydrogen-hydrogen correlation that we can see the vicinal hydrogen that are coupling by a scalar coupling. So we can see this to our example, that's lactose. This hydrogen from the galactose terminal non-reducing end can coupling to this hydrogen. The main information that COSE will give to us is this correlation. We will have a correlation of H1 to H2 from the molecule. So because this is, we did to determine the block that are coupling the same bond. In toxic analysis, we have this scalar coupling between all the hydrogens that are near to the other by a carbon bonding or nitrogen bonding, but normally carbon. And in our example, this H1, if you apply the perfect conditions, we can see the H2, we can see H3, because they are sharing hydrogens by a scalar coupling. So we have carbon here, carbon here, carbon here, carbon here, carbon here, carbon here. If you give the appropriate conditions that this nuclei spin can interact during the scalar coupling, we can see the correlations of H1 to H2, H1 to H3, H1 to H4, H1 to H5, H1 to H6. Okay, but toxic is very, very, very important to see if the connections are in the same structure. But we cannot see this type of connection, hydrogen 1 of galactose with hydrogen 4 from the glucose in the ring, because they are not sharing this. Because here we don't have hydrogen. The oxygen, we not have hydrogen. And it's impossible to coupling this to this by this, because there is no hydrogen here. So to have this information, we use the longer range experiments like HMBC or NOE. But before, we can see also the other heteronuclear experiments, like we have in the case of HSQC, because HSQC for us is very, very important. In many structures, the hydrogen in the spectrum are overlapped. The width to observe the frequencies of hydrogen is very short, different from the width and the window to observe the frequency of C13 NMR. The window is 100 more greater than the hydrogen, and the frequencies are able to split in peaks that are very, very, very separated, different that from hydrogen. So in the case of heteronuclei techniques, we have the hydrogen in the SQC that are coupling directed to the carbon that are linked. So we have this correlation, H1 to C1, AD2 to C2, and we have a correlation that is in a chemical shift map containing C13 and hydrogen in a two-dimensional spectrum. So we can monitoring this primary order, first order coupling by HSQC. And you can map all the structure by separation in two dimensions, C13 and H1 hydrogen. Using HMBC, we can correlate this hydrogen to this carbon because the experimental problem to see a long range coupling, two coupling or three coupling. We can see that the hydrogen pass to the carbon, pass this magnetization for the oxygen, and you reach the carbon that are leaked from the glucose, and we will have the carbon 4 from the linkage. Well, in our experiment, we can also have this information in special interaction of spin, because this spin is, it has a magnetic field, and this also has a magnetic field. If they are close to 3 or 2 angstroms, they can interact and alter the magnetic field of each other, and we see a correlation between both, and we can determine the linkage of the oligosaccharide. So I will pass for another slide, but I hope that some characteristics that we use to determine structure and conformation are explained in this slide. Well, for this we use NMR to analyze wine, and of course we are interested to observe the polysaccharide in wine, because wine is a interesting beverage. We consume it from 4,000 before Christ. We have some evidence that wine was produced, and this beverage has a lot of benefits in small quantities. We know that many of them are attributed to tannins, flavonoids, and other special antioxidant molecules. But the most nowadays is resveratrol. Resveratrol was present in wine, red wine, and the quantity is very, very small. But there are many biological activities that are attributed to him, but the quantities is not high. How can we determine that resveratrol is the molecule that are involved in this process? For cover the dosage that the dose that are adequate for the can I say to protect the heart, the coronary heart, to prevent body clot, and many other biological effects of resveratrol, we need to consume 1 gram per day of resveratrol. This quantity is like similar 1 ton of grape or 500 liters of wine it's impossible that this content, this amount of resveratrol should be the only organic compound involved in these very, very good properties. And also we have the French paradox that they don't have many problems with coronary attacks, and they ingest a lot of fat, and also do smoke, and they have low incidence of coronary attack. This is very, very interesting. And of course, the resveratrol, the wine also can decrease the LDL and increase HLDL. So wine is very, very interesting to understand. And for us, there are few works that were did with NMR to study polysaccharides from wine. And we try to understand these molecules using NMR and of course, the anti-inflammatory activities from the polysaccharides. So this is a simple model. We have grapes, and the grapes are smashed, and this grape smashed are put in the tunnel to ferment and other things, but we're interested in this. So in the fermentation, we have bacteria, mold, yeasts, and of course, a lot of organic compounds. We have DNA, RNA, proteins, metabolites, and glycan, polysaccharides. Many of these polysaccharides, of course, are from the grape, and of course, are from the yeast and the bacteria. But we're interested in wine. After the separation, the fermentation, and very huge pH and temperature control to provide a high quality wine, we will have certainly that many structures are in the mixture, but we will focus in polysaccharides. So we expect to see the polysaccharides from the grape. So we can see the presence of arabinogalactans type 1, arabinogalactans type 2, raminogalacturanans type 1, raminogalacturanans type 2, and polygalacturanan. In less quantity, we will see the xyloglycans and xylans, but we can also see some cellulosic compounds like galactomannan, glucomannan, and beta-glucan. These are from grape. These polysaccharides will be from grape. The structure is very complex, but for an example, in the case of arabinogalactan type 1 we will have a linked chain of galactopyranoside by beta-1,4 linkages and substituted by arabinose in carbon 3. This is an example. We have many information here, and I cannot talk a lot about this, but we have these polysaccharides, and we also have other polysaccharides. Dextrins belong to the bacteria fermentation. So if you don't have a good fermentation or control the temperature, you can favorite the growth of the bacteria, and this molecule will increase in the mixture of content of polysaccharides in wine. And of course, we will see also the monoproteins, the mannans, that are from the yeast, the cell wall from the yeast. So we have a mix of molecules that are transformed during the fermentation. We have enzymes that can cut the polysaccharides. We have organic acids that can break some time bonds that are sensitive to few degrees of pH. And we have also enzymes of bacteria. So we have a lot of compounds that can be altered. And for me, to study this mixture is very, very, very nice to observe by NMR, because you can look for metabolites, and in our case, in this work, for polysaccharides. Well, after we did the purification, the extraction, we can see example of the difference of the polysaccharides studied of different grapes. We use the Cabernet Franc, we use Cabernet Sauvignon and Sauvignon Blanc. These both are red wines, and these are blank. So we can see in C13 NMR, the complex signals here from the glycoside linkages. They are different. Of course, they are in the same region of the spectrum, but they are different. We can see also an expansion here from the region of the raminogalacturananes, that the signals of the raminols and the presence of acetyl groups in the case of Sauvignon Blanc. And we can see these different features using C13 NMR. But I will focus here on 2D spectrum, because you need a small quantity of sample, and the signals are more, how can I say, spread in 2D dimension. After purification using Fehling precipitation or complexation of mannan to copper 2, we can obtain the mannan separated from the supernatant that will have arabinogalactan type 2 and raminogalacturananes. So we can do the shifts and determine the correlation map, and we can look that these signals are from mannan. Of course, they are here, but if you see in 2 dimensions, it's more easy than see the complex signals and the peaks overlaps in 1D dimension. And of course, using some simple chemistry, we can separate and determine what type of compounds we are looking and we are interested to observe. And we separated these 2 compounds. We can see the total content of arabinogalactans here. This signal at 109 belong to arabinofluorescence units. This signal in 102 ppm and 40.5 ppm on hydrogen belong to galactan, and we can see that we have an arabinogalactan type 2 in the structure. And we can discriminate all the structure using this approach. Well, to determine if there is some difference, we also perform a total hydrolysis in the polysaccharides, and of course also in the precipitate and Fehling supernatant. And we can see the presence of Cabernet Franc. The components mainly are galactose, arabinose, ramenose, mannose, glucose are in high quantities. And we can see that galactose and arabinose belongs to arabinogalactan that we can see in the by NMR. And the wines are different in composition. We can see the galactose are different composition. Also, arabinose is different composition. And here the we can see that in failing precipitation, we have 100% of complexation with copper, and we have just one mannan. It's interesting that Sauvignon Blanc, we have a lot of content of mannan. So we can corroborate the data from NMR together with GCMS. Well, going very, very deep, looking for this region here that we determine the glycosidic region, C1, that is different from the other region, that C2, C6, we can see different fingerprints for different wines. And here we painted with the different type of polysaccharides. We have arabinogalactan, raminogalakturanan, dextran, xylan, and mannan. We can see that Cabernet Franc is totally different for Chardonnay. Here is the mannan content from Chardonnay, and we cannot see some other stuffs like dextran. And we know that this wine have some problem with temperature, so we increase the polysaccharide content provided from bacteria fermentation. These are the dextrins that we can see. Using this approach, we can create a fingerprint, and we conclude that each wine is singular, each wine is different, but it's possible also observe and study what are the how can I say, the effects of this wine, according to biological activities. So we can see that the wines, these polysaccharides, have anti-inflammatory activities. But first, we test against the cell viability, and the polysaccharides are not toxic, and we can see using MTTSA, and all of them are very good for the cells, so there's not toxic effect. And we also observe the expression of pro-inflammatory cytokines, and we can see that the polysaccharides, when stimulated with LPS, decrease the count of TNF, nitro oxide, and IL-1 beta. So this is the control, the vehicle. This is, we can see that the polysaccharides of all the wines that we test are improve the decrease of these pro-inflammatory cytokines. We also test if using just one grape, Cabernet Sauvignon with different vintages have the same polysaccharides. So this is very interesting to observe the fermentation is in very good control. And this is our question. Our question to observe is that if polysaccharides are able to use in control of the production of wine. And we tested sample from 2014, 2015, 2016. And we can see in the hydrogen spectrum that are very, very, very similar. When we look for an hydrogen 1 that represent the linkages of the polysaccharides, we can see that they are very, very similar. Also, when you look for the raminose signal from the raminogalacturanan, we can see that they are very similar also. So when you fit this structure, this spectrum, this spectra, we can see that they are very similar. And using HSQC, we are able to quantify the content of arabinogalactone, type 2, RG, mannan, and dextrin. And the content and yield are the same, basically the same, are very similar. But when you see by the integrals, the content of these polysaccharides, they are very, very similar. So we can talk that we didn't taste this wine is by an expert enologist, but we can see that this brand is very, very, very well controlled in terms of polysaccharides, because we didn't see the difference in content of dextrins and that are bad for wine. Well, also we corroborate these results using total hydrolysis and study the monosaccharide composition, and they are very, very, very similar. And we also go to understand the in vivo analysis if these polysaccharides are able to produce some effect, anti-inflammatory effect in rats. And we can see that using the model, acute sepsis model, we provide that the polysaccharides are able, and we test in oral and also by subcutaneous administration. And in this experiment is not very good, but not very good. The problem is that we kill the animals. We count how many animals are dying in the experiment. So in acute sepsis, we know that if you reach acute sepsis, you will die. In the case of rats, we test this, and you can see that polysaccharides are able to have a survival rate in a small dose, and we have this 10 milligram dose are able to prevent the animals to die. And more interesting, if we use this subcutaneous, the dose is less, and the rats are able to survive with less dose of polysaccharide. This is very, very, very interesting, because this is in vivo test. And we also measure the cytokine, and we can see that the TNF for polysaccharides are decreasing. Of course, there is a decrease of IL-1 beta, and increase of IL-10, that's an anti-inflammatory cytokine, and the decrease of the 3 inflammatory cytokines. In the pathological studies, we also observe liver, lung, and kidney, and we can see that this is a sham group. This is our control. That is a fake operated, false operated animal. And you can see that the polysaccharides, we have in both oral administration and subcutaneous administration, there is no necrosis signals that are provided by acute sepsis in lung, in liver, and in kidney. But the vehicle that not contain the polysaccharide, we can see the effects of the infiltration, of the apoptosis, and the necrosis. We can see there are huge alteration in these tissues. So we can corroborate our results that the polysaccharides are doing a very, very good effect to prevent inflammation in acute sepsis. Well, I prepared a lot of slides, but I think I went very slow, and I will finish here. And I go to the final ones. Sorry. And I will want to acknowledge everybody from CIATEJ by the invitation. And of course, I want to acknowledge my students and our group, the funding agents, CNPq, CAPS, FINEP, our university, and NMR, and some industrial partners, Kinmaster and Solabia, and our magnets that are able to do all these results that I show to you in this talk. So I thank you again. Jorge, thank you for this opportunity. And I hope in another talk I can show more about the glycosamine glycans. Thank you.
Thank you very much, Guilherme, for your excellent and interesting talk. Now we turn to questions from the public. You can open the chat to see, we have 2 questions. You can open the chat, Guilherme, if you can. I read the question. You can stop share if you want.
Okay.
In the first slide, you show us that big molecules have low NMR signals. No problem. So if we have a high molecule weight polysaccharide with an average molecular weight of 1,000 kilodalton, even bigger than proteins, NMR can be used to characterize it? You see the question?
Let's see, I'm seeing the question now. Yes. If the problem with the size of the molecule is not only the size, but you have to understand that the motion of the molecule is important. Normally, molecules around 1 million Daltons we can observe, like hyaluronic acid. Hyaluronic acid can be provide NMR signal, but you have to increase the temperature of the system. Normally, we use room temperature analysis, but in the case of hyaluronic acid, you have to decrease the viscosity. So you increase the temperature and you also decrease the concentration of the sample. In these conditions, we can see the signals of hyaluronic acid that has a mass around 1 million Daltons. So in the case of 100,000 Daltons, it's possible to observe by NMR.
Thank you very much. You can read the second one. In the case of 1, has sugar been compared before and after fermentation?
Well, very nice question. Of course, we did some laboratory experiment to observe the polysaccharides from grape. And we can provide this information that are basically the same, but the size and the viscosity of these molecules are very, very small compared to the original from the grape. So the wine mixture, in the wine during the fermentation, the polysaccharides are similar, but we believe that many of them are cut by enzymes, but the blocks continues containing the information of the whole structure of the grape polysaccharides.
Thank you. And the next 2 are my questions. Wine polysaccharides showing health benefits that has a fingerprints in NMR had a taste fingerprint. You try it?
So I think my test by fingerprint, the health benefits, we try to do something in, but not with resveratrol. We use the polysaccharides in animals, like you see in the presentation. And we use all the polysaccharides that we have produced, but I cannot affirm to you that we have a fingerprint to control if the benefits are okay.
Okay.
A test, a very deep test, a deep test should be done. But for me, it's easy. We tried use these polysaccharides from pectin from other plants, and they are not able to produce these effects. The structure are different. You have sometimes the similar backbone, but the nature of the side chains are not similar from pectin from orange or pectin from apple. They are different. But I understand your question. I think that we can test some apple juice polysaccharides and also some polysaccharides from orange. But we know from literature that they don't have this effect to modulate the immune system.
Okay. And one that for me is more funny, how many glasses of wine should you drink per day to have the health benefits?
Well, I believe that one glass should be good, but two glass is better.
Okay. Thank you. And the last one, you can read. Do you think
Yes.
it is possible with this technique to identify the place where the grapes were harvested for the production of wine?
Well, there is some other type of NMR experiments that we know they are naming the sniff NMR, that you can measure the deuterium from different regions, because we know that during the grape growth, the content of deuterium is different from France, from Spain, from the other countries in the world. So you can measure the deuterium content and compare to some wine from this region, and they are very close in terms of in content of deuterium. So if you use sniff NMR, it's possible to observe. I think that our approach can give us a signature from a singular wine, and we can use to control the production and the homogeneity of the production, more than use the origin of the wine. Origin is very nice to see some adulterant, to see if somebody is putting wine from Portugal or wine from another country and mix together, and okay, we have another wine and we can export them. I think this different NMR is better, but to see the homogeneity of the product of the wine and control production, if you have a great wine, I think polysaccharide could be a good choice.
Thank you very much, Guilherme, for your talk, and everyone for the question. For the time, we need to close this conference, and we hope to have the opportunity to visit Guilherme, and also you can visit CIATEJ to see what we do. Muito obrigado, Guilherme. Vamos a continuar con las siguientes conferencias. Nos vemos pronto, Guilherme. Un saludo, un abrazo.
Saludo.